Welcome back to ECE 320A, one day before exam number 3. Our final exam is coming. What? Oh, Thursday. I don't know what I'm saying, obviously. The exam is the next time we meet, and that is Thursday. And there is review material if you would like to take advantage of that. That's on D2L. We had our review session last night. That was Monday, I believe. And that should be posted and available. Today what I want, and homework number 8 is also due today. And I should be able to post the solutions to that shortly after 4, well, maybe at 5 o'clock. I think I have a 4 o'clock meeting. So make sure you get your homework turned in either in class or in my mailbox by the appropriate time. And the solutions, I'm somewhat verbose on those, so you might read those. Maybe I did it in hopes that you would maybe get a little bit more out of it than me just writing down sort of quick answers or short answers. Today what I want to do is just review the policy for exam number 3, or the process, which is consistent with the previous exams. We will review h of j omega, how we determine that graphically. That's really to sort of get us thinking, one, in terms of the exam, that material is exam related or can be on the exam, and 2, it sets the stage nicely for Bode plots, which is when we want to actually create h of j omega magnitude and phase information for all frequencies. That's really all we're doing. Is if you walked up the imaginary axis point for point and recorded each of those magnitudes and phases, then you could really sketch the Bode plot. That's what the Bode plot is doing, or it's giving you a frequency response for a given system, and we'll try to motivate that or show that or illustrate that via simple examples. As I said, the exam process is consistent with what we've been doing all along. You have the front and back now of 3 sheets of notes for exam number 3. If you need that many sheets, I would just bring the minimum number that you are comfortable with or that you actually need. You don't have to have all 3 sheets if you don't need them. But if you want to add to your existing 2 and it's easier, then create a 3rd sheet. You can have any calculator, and please bring something to write with. Are there any questions on the exam? What topics are covered in very quick terms are homework sets 6, 7, and 8. And in topic terms, it's sort of in reverse order: convolution, transfer functions, and S-domain circuits. Question? Frequency selective circuits in terms, so the question was, what about frequency selective circuits? Yes, those could be in terms of finding the transfer function or writing. It's not really designing frequency selective circuits. But homework 8 material is okay for concepts and content for exam number 3. And that's coming from chapter 14, which is maybe labeled frequency selective circuits, but we're in a position to do at least what we've done on homework number 8 for exam number 3, if that makes any sense. If you're looking at old or practice exams, please don't just isolate on exam number 3. Some of the stuff in exam number 2's practice is also fair game for our exam number 3 this semester, just as a heads up. Questions on exam 3, or what to expect, and that's the next time we meet. Let's start then with this sinusoidal steady state idea of maybe more quickly finding the sinusoidal steady state output response given a input sinusoid, in this case it's a cosine, and a transfer function h of s. And at some point beyond exam 3, which is the final exam, I might give you not h of s, but I might sketch a Bode plot and ask you the same question. Find y steady state of t. Now you can basically, using the Bode plot, you can find it for any frequency you're interested in, as long as that frequency is indicated on the Bode plot axis that you're given. And hopefully that will start to make more sense after today's class. Here is the problem, and what I'm wanting to illustrate right now is how we actually can address this problem graphically. Here is our S-plane. I'm taking steps of size 2 in my sketch, which now allows me to place a pole at -10. I really wanted to make that a different color. And I have a 0 halfway between my tick marks, or at -1. That's the pole 0 diagram. That's as complex as it gets for this transfer function h of s, which if you take a controls class, somebody might say, oh, that's actually a phase lead controller, and that will mean more to you in that class, but we will use that transfer function to illustrate this particular design. Now that's some system that is processing this sinusoidal waveform. Given that input signal, x of t, what do we need to immediately start concentrating on from that description? The 6, right? The omega, the frequency. This x of t immediately should be saying, oh, we need to be concentrating on this frequency of 6 radians per second, which is about 1 hertz in terms of frequency, since that's 2 pi f. And 2 pi 1 would be 6.28, so it's roughly 1 hertz. We're exciting this system, this 30 s plus 1 divided by s plus 10 at 1 hertz. So that's going up and down at 1 cycle per second, roughly. That means we can now walk up or underneath the circus tent and focus on what's happening at J6 on the imaginary axis. We want to now, we could be standing there and we could say, okay, what's the pole contributing, what's the 0 contributing, and what angles, in terms of what are their magnitudes contributing and what are their angles contributing to this sinusoidal excitation. And we can graphically think about that really sort of using these line of sights between the singularities, the 0 and the pole, and that location of interest, which is determined by the frequency that the x is moving at, which is 6 radians per second. This length we'll call L sub p. This length we'll call L sub z. That angle is theta sub p. And these angles, remember, are measured with respect to the positive horizontal line, the line horizontally to the right. And with that information, which if my sketch was drawn accurately, I could measure those physically from the graph and not have to get out a calculator if I wanted to. I could simply measure those lengths and angles and use that to determine what I need to find. What I'm looking for now is h of J6, and it's important actually that my transfer function be written in pole zero form, which it is. These factors are zero factors and pole factors. That now is consistent with this pole zero diagram and the computations that I'm now going to I can scale that by the length from the 0 to J6 and divide by the distance from the pole to J6, and that's now my magnitude of my transfer function at that particular frequency 6. And my angle of h of J6 is simply I take all the zeros angles, and I only have one unless you want to consider the angle of 30. What's the angle of 30? If I just said the gain has an angle, what is the angle associated with 30? 0. If it was minus 30, then its angle would be minus 180 degrees. I just say minus 180. It would be equivalent to say plus 180 because it gets you to exactly the same point. But I like minus 180 because then it can sort of be thought of as a delay instead of an advance when you put it in the argument. That's the only reason why I specify minus 180 degrees. Question? I'm not checking stability, so I don't have to be positive and present, right? Sorry. Question? So L sub z is the magnitude of, it's really this right triangle that we've created, so it's maybe not clear from my diagram, but it's the horizontal distance of 1 and the vertical distance of 6. Those are my sides of my right triangle, so it's the square root of 1 squared plus 6 squared. That's L sub z. Did that answer your question? So I'll try to be a little more positive, but I'm talking about poles now, and I can't because they're in the basement. They have to come in with a negative sign. So I subtract the angle contributed by that pole. And that's now, if I can find those numbers, I can now use that to create my output sinusoidal steady state response. Meaning L sub z, if it's not clear already, that's this square root of 1 squared plus 6 squared. L sub p is the horizontal distance squared plus the vertical distance squared. So we have the square root of 37, which if my calculator was giving me, if I plugged in the right number, that's a little bit more than 6, which makes sense. That's supposed to be 6 squared under the radical down below. So that's the square root of 136, which is a little bit bigger than 10, or 11.662. My angle of the 0 is now, the vertical distance is 6, the horizontal or adjacent side is 1. So I'll try to be explicit in how I'm defining that theta sub z. That's a pretty good size angle. It's 80 degrees. How much could a 0 contribute angle? What's the maximum a 0 could contribute? 90 degrees. You would have to be looking all the way up. Or as you get way up there in frequency, that 0 is effectively contributing 90 degrees. Likewise with a pole. A single pole can contribute 90 degrees. It's just in the basement, and so it will be in minus 90. And that's what we need to work on understanding or using when we start sketching these Bode plots. But theta sub p is now we go up 6 and over 10 to now have the inverse tangent of 0.6, which is not quite 0.7, so it should be a little bit less than 45 degrees, just as a way of keeping track of all of this. If we now plugged all of that in up here, we should end up with the answer being, the magnitude is 15.65, and the angle was the 80 minus 31, or a little bit more than 49 degrees. Is that making sense? So if we shake this particular system at 1 hertz, 6 radians per second, a rough 1 hertz. If we shake this system at 6 radians per second, that's the h of J6, then that system will amplify our shake by 15.65. Yes? Yes, so this is equivalent to taking the h of s wave or description, the h of s representation, and replacing s everywhere with J6. That should give you exactly the same polar form of the complex number h of J6. And if it doesn't, then we've done something wrong. Question? Pardon? Why does this work? It's magic. So what we are doing is we are trying to evaluate h at a given frequency, j omega, and the way that we are doing it, it should make sense to you. If we now replace h of s with s equal to j omega, we replace all these s's with j omega, then the magnitude of the denominator is just the magnitude of j omega plus 10. So if we look at that and we say, oh, here's 10, and here's j omega, in our case actually 6. So we're looking for the length of 10 plus J6. And that's just this hypotenuse. That's LP1. And that's the bottom magnitude. That's due to the pole. And we're doing the same exact thing for all of our poles and zeros. But we do have to keep the transfer function in pole zero form, and we need to make sure we account for that gain. Likewise, the angles. That's why the angles work, is we look at all the angles contributed by the zeros. Those are upstairs, those sum, and then any pole angles, which are downstairs, those subtract, just like we do with complex numbers. Yes, question? Yes, if you had multiple... I'm sorry, I cut you off. Okay, so the question is, if I put another 0 in here, let's say at -4, which I really wouldn't want to do in a design scenario, because now I have sort of a differentiator circuit, but I would want to pair that up with another pole so that I wouldn't be differentiating, which differentiating, if you had a noisy signal, a differentiator at high frequencies is going to go unbounded. And now if you have a noisy signal, which is high frequency, you're just exaggerating that. But anyway, more than you wanted to hear. Yes, your answer is, if you had another 0 at -4, you would have another length, let's call it L sub z sub 1, and you would multiply that times L sub z. So all of these are simply factored together, meaning if I now had, I really feel a little bit nervous about doing this. What did I say? That was an s plus 4, and so that gave us that right there, and this would give us a different length. And all of those factors, then, we look at the magnitudes, their lengths will be multiplied or divided if they're zeros or poles, and their angles will be added or subtracted. Does that make sense? So we add and subtract angles, we multiply and divide magnitudes or lengths for all of the factors that we might have. I'm going to clean this up just a little, and I'll probably make more of a mess than I wanted to. Other questions on that? If that's h of J6, then our sinusoidal steady state output needs to incorporate that information into x, which says that we simply scale the output, the output's magnitude will be the input magnitude scaled by whatever h gives us. In this case, it's a scaling of 15, or a little bit more. and it'll shift its phase or its angle by whatever the angle contributes in that transfer function. If we do that, we now have then for a result, we have 2 times whatever I just said the magnitude was, 15.64 cosine. We can't change that. That's going to be the same. The frequency, it's a linear system. We have a transfer function, so the frequency we are not changing. That's still 6 radians per second. But what we are do is changing that relative to the x of t waveform. And hopefully I'm using the right numbers. That's then the output response for that given input excitation and transfer function, capital H of S. And this gives us actually a net phase increase. This is sort of an advance. So if you sketch these waveforms together, x of t would actually be behind y of t in the sinusoidal steady state based on these angles. Yes? So the question was, does this work if x, which is what we're starting with, is what we're exciting the system with, does it only work for a cosine or does it work with a sine? The answer is it works with either one. You just have to maintain that argument or that expression in your answer. Meaning if you start with a sine, you better end up with sine so that you keep your phase shift correct. But if you don't feel comfortable with that, then immediately convert your sines to cosines. And then say, okay, now I have a cosine waveform. And it'll just be different from your original sine by 90 degrees. So you keep that argument in there in addition to whatever your system shifts you, either positively or negatively. That answer your question? Yes? Yes. So now the question was, and we would have gotten the same answer had we gone the long way. And the answer is sort of. We would have gotten more, wouldn't we? We would have gotten more information if we would have found all of capital Y of S's inverse Laplace transform. Does everybody understand what I'm saying? If we looked for the complete or total solution for Y of t, and we say, oh, there's 0 initial conditions. Let's say there's 0 initial conditions, no energy storage. What's the complete Y of t? You could find that by Laplace transforming x of t to get capital X of S, which is pretty easy to do, I hope, by this point. What is that? Whoops, it's not H. What is that? That's the Laplace transform of a cosine, I hope. Is that true? What? Okay, so the cosine has the S in the numerator. Sort of just kind of remember that, okay? And you'll have it on your tables for the exam. But you could now take that capital X of S, multiply it by H of S, and now do a partial fraction expansion. And what are you going to have in addition to what we just created? You're going to have the transients, aren't you? And how long are you going to have to wait before those transients are effectively gone in this case, in this system? 5 seconds. Any other answers? What is my time constant of the transient? And so I could ask this many different ways. I could give you H of S, I could give you the pole zero diagram. Either one, and I could ask you this same question. And I could give it to you as a convolution problem. I could say, here's your X of t. When practically are you going to quit seeing an output? And you would be saying, oh, 5 time constants after the slowest mode in your system. And what are my modes of my system? How many do I have? How many, if I did this by the convolution approach, what would I need? Your impulse response, little h of t. What would you get for h of t here? This is why this is kind of a weird one. First, you would want to remember your rules, right? What does capital H of S have to be? Proper, or what I like to say, strictly proper. The denominator degree has to exceed the numerator degree. So you'd have to divide your denominator into your numerator to begin with and get rid of that one term or isolate that one term, and then you have this other part that is strictly proper. All of this should start to be sounding very familiar. You have to know it for the final. Okay, and this is getting kind of fun, I think, isn't it? This material. We can do a lot. You now have the ability to do a lot, whether you know it or not. You have a lot of skills, a lot of talent. Don't let anybody sell you short. Okay? But if we simply concentrate on what's in the denominator, what are we going to see? What kind of a transient term? What kind of a structure is going to result from this system? We'll have an impulse because we have a constant, right? So that h of t will have an impulsive behavior, which just means that, oh, it's going to sort of excite all my energy storage terms and give me something that is maybe a little odd. But if we forget that for now, and I just say, what's the transient term? What is it? Where's my pole? Minus 10, isn't it? It's at minus 10. So I have this mode e to the minus 10t. What's the time constant of that mode? 1/10. So now I need 5 of those time constants. My time horizon after exciting this system is a half a second. 5 times 0.1. Is that making sense? I would only have to wait a half a second before I reach sinusoidal steady state effectively. Other questions on that? Let's start talking Bode plots. Now what we want to do is, instead of doing this point for point, see that triangle? We could theoretically march that triangle from 0. If we evaluated this at 0, that would be our DC gain. If we go up here, then it's J.1, J.2, J1, J2, etc. If we did that for all of the points on the imaginary axis, that's the content, that's the information we want for our frequency response. That tells us how this particular system responds to any given signal. And if you wanted to physically measure that, you could excite it at a frequency, wait for the transients to decay, and measure the magnitude and phase. Shake it again at a different frequency and do the same thing. Wait for the transients to decay, measure the magnitude and phase. We want to be able to do that more quickly than doing that point for point. But you could now do that if you wanted to with your calculator or with MATLAB if we're learning MATLAB. Let's now look at doing that from a more one process. It involves many steps, but we want to do this now more all at once. We want to create the magnitude as a function of frequency and the angle as a function of frequency. To motivate this, suppose that we have the following, and this is somewhat of a review, but you now should be getting very comfortable with analyzing op-amp circuits. say that's our load resistor. This resistor in the input direction is R sub 1, the feedback resistor is R sub 2, and a capacitor, and here is then our input signal V sub I. And what I want to do is find the transfer function for that circuit and then sketch its frequency response. How does this system behave as a function of frequency? You could build this in the lab, excite it with different V sub i's at different frequencies, and measure the output, and that would then give you the frequency response experimentally. If you're getting confused, just think back at that and say, I'm just creating, I'm seeing how this system either enhances or attenuates certain frequencies and how it shifts them in time. That's all we're doing with the frequency response. But once we have that frequency response, that tells us a lot about our system. How can we do this? Well, if you feel comfortable simply analyzing an inverter circuit, we could simply say, well, let's just make that a feedback impedance. And now I have really an input impedance and a feedback impedance, and I can just apply my expressions or formulas of the inverter equation. Z sub f is now simply R sub 2 in parallel with this capacitor, 1 over SC, and if I do that, I now have R2 times 1 over SC, and I have the sum of those two. If I find a common denominator in the numerator and a common denominator in the denominator, it's exactly the same. It's SC. Those two will cancel, and I will end up with R2 over S, R sub 2 C plus 1. That's my feedback impedance expression. If I now go back and I say, well, what's my transfer function between V sub I and V sub O, I could now say, well, let me write KCL at that inverting terminal node. And I know if this is not saturated and I'm in ideal conditions, there will be no current going into that inverting terminal node or terminal. For that reason, I only have two currents to worry about in the KCL equation. And if I do this in the frequency domain, I now have the current going to the left. If I say KCL at V sub n, hopefully that's clear what I'm trying to say. I now have V sub n of S minus V sub I of S all over R sub 1. That's the current going to the left from that node. That should be clear. And then I have to worry about the current going to the right, which is V sub n of S minus V sub 0 of S over Z sub F, and those sum to 0. And if I'm dealing with an ideal non-saturating circuit, I know that I have this virtual short between my two terminals effectively, and so V sub P is the same as V sub N. V sub P is grounded. V sub N then is 0, and I can get rid of V sub N in my previous KCL equation. I can set that equal to 0. And now I end up with this V sub 0 of S over Z sub F is equal to minus V sub I of S over R1. This is a review. If you don't feel comfortable with this, you need to by Thursday, because this is a valid problem I could ask you on the exam. I could say find the transfer function between V sub I and V sub 0, or I could say give me the poles and zeros of this circuit, etc. A lot of different things. I could even say give me the sinusoidal steady state output. Now I could say find the frequency response at J2. And you should be able to do that also. Do you see how many problems I can shuffle around and produce just by giving you one diagram or circuit? In this case, I now have V sub naught of S over V sub I of S. That's my transfer function. That's simply minus Z sub F, which is a function of S, over R sub 1. And my Z sub F of S, I've already computed, and that was R sub 2. Let me go ahead and divide that by R1, and then I had S R sub 2C plus 1. And that's now my transfer function. And if I didn't like that minus sign, I'd maybe put this into an inverter circuit. And then I would not have to worry about that minus sign, and I would simply have a transfer function H of S that didn't have that minus sign in it. Is that okay? So I'm going to play fast and loose with that minus sign. I'll probably just neglect it. But what do I have now? From that simple op-amp circuit, you've now created a filter. What kind of a filter is this? If you had to describe it, is it a low pass? Is it a band pass? Is it a band reject? Is it a high pass? It's a frequency selective filter. Can you tell from what you know right now? So now just look at some limiting cases. So now just think about this and say, well, what can I talk about? What if I wanted to say, what if I said, what's the DC gain of this circuit? Could you tell me? You let S equal 0, and this is in time constant form, which makes that nice. Now you just have 1 in the denominator. This now, all I have to worry about is what's in the numerator for my DC gain. My DC gain is negative, so it's going to invert whatever you put in at DC. That's why I said I might just forget about it, but it would be important if you didn't put an inverter on here again to give you a positive gain. But now your amplification is R2 over R1. Your DC gain is R2 over R1. So now that's some number. Let's say R2 is a factor of 10 bigger than R1. You now have a gain of 10 at DC. What kind of a gain do you have at high frequencies? And if you're saying, okay, if I'm looking at the frequency response, what are you doing? You're now marching along the imaginary axis. You're replacing S with J omega. Now you have J omega, R sub 2C plus 1. You're saying, what happens when omega gets big? What happens to your denominator? It gets really, really big, doesn't it? What does that do to your overall behavior of H? It collapses it, doesn't it? It shrinks it. So at high frequencies, this transfer function is getting smaller, very small. So it started at some value, and then it got small for high frequencies. What kind of a frequency selective device is this? Just by using those two, it's low pass. So now you know that this is a low pass structure. Yes? And so what is our cutoff frequency? Where does this transition occur? Or where do we approximate it? We approximate it where, in this case, what's the order of this low-pass filter? 1. We only have one pole, right? S to the 1. We have one pole. This is a first-order low-pass filter from that op-amp circuit. We built a first-order low-pass, so now it's an active device. We have an active filter. Because it's first order, we can definitively define what the cutoff frequency is, and that's this transition between its flat response and where it rolls off. And we define that to be at the corner or break or the cutoff frequency, and that's at the pole. And where is our pole in this particular system? Or how do we find it? And you could just go back to the definition of a pole. Well, a pole is supposed to make H blow up. Well, to make H blow up, I need the denominator to vanish. If that's the case, then you're looking at the value of S that causes that expression to be true. You're setting the denominator factor to 0 to find your pole. And in fact, what was this? What have we called this little product before? Tau, our time constant. And if we now look at this, our pole is now just the reciprocal of that time constant. It's minus 1 over r sub 2c. So if somebody said, oh, I want my low-pass filter to have a bandwidth of 2 radians per second, maybe you've already picked R2, or maybe you have to live with what Josie has in the stockroom. And capacitors are probably more precious than resistors in terms of finding one, so you're stuck with a capacitor. And the homework, what was it, 4.7 microfarads that you had to live with? So now you're given that, and now you need this 1 over r sub 2c to maybe be 2 if you wanted a low pass with a cutoff frequency of 2 radians per second. You would want 1 over r sub 2c, that product, to be 2. You'd need to pick your resistor appropriately. Yes? So now the question is, we're getting ahead of ourselves from what I wanted to talk about today. What if you had 2 poles? Then, what's going on? This is fun though, isn't it? So now we have 2 poles. What's going to happen? You're going to be going along, and if you wanted to create a low-pass filter, you might put them right on top of each other and have them both cut off at the same frequency. You may say, oh, let one be at 2 and the other one be at 2. And then I'm going to fall off more rapidly because I have 2 going instead of 1. But if you don't, then you'll have a break, and then you'll have another break. And you'll just say, well, my low-pass filter bandwidth is where I get my first break. And then your next break is wherever it is, wherever your other pole is. So now you have, in terms of our Bode plot, you're going to have these 2 transitions depending on where your poles are located. And hopefully that will make sense if we get that far, but I'm going pretty slow because I'm so excited about what we're talking about. Is this okay? Everybody get this. So our pole is at minus 1 over r sub 2c. What's our, and we've already talked about our DC gain. Our DC gain is found when we set S equal to 0, and that was this minus r sub 2 over r1 over 0 plus 1. Or it's that. Now, in order not to keep all of those, keep track of all of that, let's just make this more generic and say, okay, let's just say that we have some gain K and some time constant tau. And this is now a first order low pass filter. Is everybody okay with that? But now you know where those come from. If somebody said, build me a low pass filter after today's lecture, you can do that. Yes? Very easily. Go see Josie, get an op amp, a resistor, and a capacitor, a couple resistors, and you're good to go. You just need to know what the bandwidth is to pick those R's and C's. But now we're just going to say, okay, let's have a gain K and a time constant tau. What's my DC gain of this H of S? Capital K. And my pole, where's my pole? Minus 1 over tau. All right. So how many terms do I have effectively in this simple example? I have a gain term, a k, and I have a linear term, that pole factor. I have 2 terms, and those are 2 that I want to talk about so that you start to get comfortable with sketching the contributions from each of these terms. What we want to do is identify certain terms in a transfer function. We'll have a constant term, we'll have linear terms. Those could be in the denominator for poles, they could be in the numerator for zeros. Then we could actually have terms that are due to poles or zeros at the origin. So if I could simply cover up that 1, I would have a pole at the origin. And that behaves slightly differently than a linear pole. Or a 0 at the origin. That behaves a little differently. But for now, let's focus on a linear factor and a constant. And we could have quadratic factors. And we'll worry about that later. The main thing is if you can figure out this, you've got a long way towards doing the rest. That's why I want to concentrate on this simple case to begin with. Let's look at these 2 terms. One term is the gain term. That's just the k. And the other term is what I'm going to call a linear term, but I will even make it more specific. I'll say for now, let's say a linear pole factor. And that's this tau s plus 1. It's linear because of that power of s. That's not a 2, that's a 1. If it was a 2, it would be a quadratic factor. Is that clear? So this makes it the linear factor, and the fact that it's in the denominator, which typically if you just wanted to treat it as a factor and you didn't know whether it was a pole or 0, you could raise it to the minus 1, and that would be, oh, that's a pole factor. So it's in the denominator. Which gives us our pole. And what we want to do now is for those 2 terms, or those 2 factors, we want to sketch their magnitude and phase contributions for all frequencies. We want to be able to sketch those. And the reason why we sketch Bode plots is it gives us a magnitude in dB. And if we look at all of these terms in decibels in dB, we can simply add their contributions. That's as simple as it gets. And angles already add and subtract. So we'll look at angles in degrees and magnitudes in dB, and that allows us to sketch each of these terms independently and then add them up at the end to get the overall frequency response, magnitude and phase. Let's look then at the magnitude. And phase as a function of omega, or frequency, for each term. And we're going to sketch this. Our independent variable will actually be log of omega. It will be a logarithmic scale. So these sketches are on semi-log paper, and I used to have you go out and go to the bookstore and get 5-cycle semi-log graph paper. Now you can simply create that in MATLAB and print it out on your computer. But you used to have to pay 20 cents a sheet or something. So boy, you wanted to be accurate. Or you didn't want to make a mistake. Let's look at the gain term. And this is going to seem so easy. Don't fall asleep on me. But now in terms of dB, to find the dB, we take 20 times the log base 10 of whatever it is that we're worried about, and in this case it's the gain k. And actually, to be accurate, we need the magnitude. If k was negative, we're really only interested in the magnitude of it. We don't want to start taking the log of a negative number because that doesn't make any sense. So we now take the log of the magnitudes of these terms, and this is true for all omega. And k is fixed. That wasn't a function of omega, was it? So once you have k, if k, well, let's try to sketch this. So here is, I get sloppy, I just label this as log, but it's really log of omega, meaning this might be 0, this might be 10, this might be 100, this might be 0.1 or 10 to the minus 1, this might be 10 to the minus 2, and that's 4-cycle log paper. I've now put 4 decades or 4 cycles in that particular sketch. And these would be uniformly spaced. I have 1, 2, 3, 4 cycles of my graph. And if you needed to know where 2 was on this, it's not uniformly spaced between 0 and 10, is it? What's the log of 2? So take the log of 2 and what do you get? What's the log of 10? 1. What's the log of 0? I'm sorry. What's the log of 1? 0. So we know the log of 2 must be between 0 and 1. What's the log of 2? Does anybody have a calculator? 0.3. So now we need to go 30% of the way towards 10 to get our 2. Is that making sense? This is, why didn't you guys wake me up? That's not 0. We don't have 0. You did? Well, you're going to have to be a little more. What? What? Thank you. Okay, that's 10 to the 0. I have selective hearing. Ask my children. Or ask anyone, probably, for that. Yeah, ask the class, right? I have selective hearing. That was 10 to the 0. This is 10 to the 1. So that's 1. This is, this is 0 in terms of log, and this is 1. Now we want to find the 2. That was 30% of the distance towards 10. Is that making sense if we needed to find that? But we're plotting 20 log of k. If k happened to be 10, that would be its contribution. That's supposed to be a flat line at 20 dB. That would be with k equal to 10. If k actually was 0, if k was 1, then we would have 20 log of 1, which is 0, and we would be right on the axis. Is that making sense? If we had a magnitude of 1, we would have a dB of 0 dB. If we said, oh, what if you have a gain k of 100? Now we have 40 dB of gain. If we had a gain k of 0.1, those are supposed to be flat lines. Is that making sense? If we had a gain k of 0.01, we would have a minus 40 dB line. And that's flat for all frequencies. That's all you have to do to sketch a gain, is locate what it is in terms of dB and draw it on your plot as a flat line. And that's the gain's contribution for all frequencies. What's the DC gain? Is that a trick question? Where is DC on this plot? Where's DC? Good thing this is not a camera. It's just the screen capture. So you'll have to remember that I ran into the wall when I was asking for 0 or DC. This never finishes, does it? 10 to the minus 3, 10 to the minus 4, 10 to the... We just keep adding cycles and cycles. We never get to DC, but the implied notion would be wherever we're starting, that's what its DC value is. Is that making sense? So if we had a gain K of 10, then if we didn't have any poles at the origin or any zeros at the origin, and we had linear terms, that linear factors or quadratic factors with break frequencies to the right or higher in frequency than 0.01, we could go back to that left side and say, there's your DC gain. That makes sense? All right, what's the phase of this K? That's simply the angle of K. In general terms, that's either 0 degrees if we have a non-negative K, and by convention, let's just agree for this class that if we have a negative K, we'll let the angle be minus 180 degrees, and that's true for all frequencies. Meaning now we are going to be sketching two graphs. We will have one graph that's the magnitude graph, and we'll have another graph that's the phase graph. So now the angle of K would either be 0 degrees if K was non-negative, or it would be down here at minus 180 degrees if K is less than 0. Questions on that? That's our gain. That's pretty easy. You just put your transfer function in time constant form and look at your gain, and now you've sketched the Bode plot for the gain term. So to sketch Bode plots, we need the transfer function in time constant form. That's the first thing that we really have to do. I told you you'd go to sleep on that gain one. Somebody was yawning. I don't know if anybody else heard that. See, I heard that, selective hearing. So you don't want to do something... Yeah, never mind. Okay. I'm trying to be positive. Really, I am. Okay. Linear factor. There's our linear factor, tau s plus 1, and we know for our case that that's in the denominator. It's a pole factor, but we can talk about these in general terms right now. And then if it's in the denominator, we go down, and we have negative angles. If it's a 0 factor, we're going up, and we have positive angles. What's the magnitude of this look like? It is frequency dependent. What I want you to do today is get a feel for what we're dealing with. We now take 20 times the log, that's base 10, of that factor, which is j omega tau plus 1. And I hope it's clear that that magnitude does depend on frequency, omega. But let's look at some extremes so that we get a feel for what might happen. The first extreme, let's say that for frequencies such that omega tau is much less than 1. So now we're comparing the real component and the imaginary component of this complex number. And the first extreme that we are going to consider is, let's assume that this imaginary part of this complex number, omega tau, is much less than 1. And we're going to now approximate that factor. So if this is true, then we have omega much less than 1 over tau. But what's 1 over tau? That's the break frequency, isn't it? It's either the pole location or the zero location. That's our 1 over tau for a linear term. So this tau is the pole's time constant. But this whole piece is the pole location. Is that clear? That 1 over tau is the linear's pole location. So if somebody said, oh, you have a pole at 2, then you know for quite a bit less than 2, we're going to be looking at 20 log of whatever that approximates to be. So let's do that. So if we are under this scenario, let's say this is scenario A, for omega tau much less than 1, then we can say that j omega tau plus 1 as a expression looks pretty much like 1 if omega tau is much less than 1. So we're going to approximate that by 1. And that allows us then to say that the magnitude of this j omega tau plus 1 is approximately 20 times the log of 1. And that's 0 dB. That means if you have a linear pole factor or a linear zero factor for frequencies much less than the break frequency of that polar zero, that factor is contributing 0 dB to the magnitude for low frequencies. And low means relative to that particular break frequency. That's one extreme. Let's go and look at another extreme. Let's say now, for, hopefully this makes sense, let's look at the other possibility. For omega tau much bigger than 1, now we are saying omega is much bigger than 1 over tau, or this is actually, in the homework terminology, that's the cutoff frequency. This is now the break frequency of a pole or a zero. So we are talking now about much larger, or omega is much larger than what we will call in the Bode plot terminology than the break frequency. It's where the magnitude plot breaks, or it's much larger than the pole location. If we had a pole at 20, then what we will consider to be much larger is a decade beyond that. And we would say, oh, at 200, this approximation is okay. That's going to be our approximation. So if we have this situation, what does this look like now as an expression under this condition? When omega tau is much bigger than 1, pardon me while I Just have a little break. Somebody was tired, so I let them have a 10-minute nap. 10-minute. 5-second nap. Now we're rested. J omega tau for omega tau much bigger than 1 becomes, it looks more like the imaginary part of that number, so it's now j omega tau. Under that condition, we now have 20 log, again base 10, of the magnitude of j omega tau plus 1. We are going to say that that's approximately 20 times the log base 10 of j omega tau. And what's the magnitude of j omega tau? We can forget the j, can't we, now, because we're only interested in the magnitude. So that j goes away. And what else do we know about tau? We could actually rewrite this Is that okay? We're going to replace tau with 1 over omega c, because omega c is our break frequency, and that's what we're interested in. And now we can go back and say, oh, I remember my logarithmic relationships. When I divide, log of a quotient is the subtraction of the logs. Now, what were we plotting with respect to before in our Bode plots? We were actually sketching our plots with respect to log of omega. That was our independent variable. And omega c that's just a fixed number. So this is simply a constant. But let's look at sort of what happens. What happens when we actually let omega equal the break frequency omega c? What happens? We can either look at it in the subtraction form or even sooner and say when omega is actually equal to the break, we have log of 1, and what's that? 0. So now in this approximation, this gets us back to where our other one gave us, which was 0, when we're right at omega equal to the break. So now we're going to connect our straight line approximations. We have this, I hope, it maybe isn't that clear yet, but this log of omega, think of that as x. This is mx, where m, the slope, is 20. That's where that 20 dB per decade comes in. And remember what I didn't do here, I didn't raise j omega tau plus 1 to the minus 1. But if I had, this whole thing would have been negated, and that pole would have been a minus 20 for a slope. Now it's looking more like a 0 factor, and it's going up plus 20. Is this making any sense? The slope is 20, and the independent variable is log of omega. So we're now going up 20 dB or down 20 dB. If we're going up, it's due to a 0. If we're going down, it's due to a pole factor. And we were at 0 dB for low frequencies. For high frequencies, when omega is much bigger than omega c, that 20 log of omega dominates. And now we want to just connect those pieces together. Is that making sense? This now says that we have a magnitude of 0 dB, and this magnitude piece now sort of looks like this 20x plus some b term, a constant. And if we now have this pole factor, that's in the denominator or in the basement. And our factor then would really be this j omega tau plus 1 to the minus 1. And this would then give us that minus 20 dB slope. So therefore, we would have 20 log of this j omega tau plus 1 to the minus 1. And you know what the exponents do with the logs. They go out front, and that's where our minus 20 comes in. So this now looks like this minus 20 times the log of j omega tau plus 1, and we can follow through all of our earlier discussion. What I want to do now is simply say, let's look at, based on this discussion, let's now sketch our straight line approximation magnitude response or frequency response for this linear factor or linear term. If we have our frequency axis omega, all we really need to do is we need to find where our break frequency is on that, and we can locate it if somebody gives us the value. Let's say we had a pole at 2, then we would locate that. If this is 10 to the 0, 10 to the 1, 10 squared, 10 to the minus 1, then this would be omega equal 2. That's supposed to be 30% of the way or distance between 1 and 10. Is that making sense? We locate that, and now what happens? Below that, we said we can approximate that by 0 dB. And this line that I've sketched is my 0 dB line. So now my sketch is going to be flat. And now I'm going to simply connect those two approximations. And the other one said that I needed to be going down at 20 dB per decade. So what I like to do is I like to come over here to 20. So here's 20. And I now march down to 20 dB below where I was at 2. And now I just get my ruler out. I told you this was fun. If you can sketch, which I can't do without my ruler. So that was supposed to be a straight line. What's the slope? I like to indicate that that's minus 20 dB per decade. And I found that by going over to 20, which was a decade bigger than 2, and going down to minus 20 and then connecting those 2 points. And now I have my straight line. And that is my low-pass filter with a cutoff frequency of 2. In fact, the actual magnitude plot looks like what? This is an approximation. If you looked at the magnitude right at the cutoff, where is it going to be? Now omega c is equal to omega. And now we have 1 plus j in the denominator. What's the magnitude of 1 plus j? So now we have a right triangle with sides equal to 1. What's the hypotenuse? Square root of 2. So now we have 1 over the square root of 2. And you see this all the time, don't you? 1 over the square root of 2 is 0.707. In dB, what is that? Minus 3 dB. So the true curve is 3 dB down at the break frequency. But all we're doing right now is worrying about the straight line approximations. This gives us enough so that if somebody now plots this in MATLAB, we say, yes, that looks about right. So the true curve would be flat, and then it would start to bend a little bit, and it would be minus 3 dB down, and then it would catch up to that straight line approximation as omega got bigger. Is that making sense? So we would be doing something like this with the true curve. And that's for a linear expression or a linear factor. What's the phase look like? Wow, time flies when you're having fun. What are we going to do? We're going to pick up after the exam with the phase of this, but you can think your way through this. You have j omega t or j omega tau plus 1. At small frequencies, what do we look like? We look at 1 and say, what's the angle of 1? 0. What's at high frequencies? J omega tau plus 1 looks like J omega tau. What's the angle of J? 90. So if it's a pole, it's minus 90. If it's a 0, it's plus 90. What's halfway between 0 and 90? 45. And that's when J, 1 plus J, or when omega is equal to omega C. We'll look at those three frequencies and we'll be done. I'll see you Thursday. Be ready to go for the exam.